Hello.
To see my screen. So yeah, we were looking at how the GPU would actually realize this data parallelism, right? Each individual iteration will be assigned to one thread, and a group of such threads, which we call warps, will be executing the same instruction. So that's what we have indicated here in warp 0. The instruction with at PC is the program counter or the address of the instruction, which is X here, will be executed. Then after that, the entire warp will move to the next instruction, which is PC, X plus 1, then X plus 2, then X plus 3, so on and so forth. So all the threads in the warp will execute the same instruction, but on different data items. Okay. Now, in interest of time, I'll skip this. And so because now we are saying that the group of threads within a warp will be called, will be executing the same instruction, there can be some, fine-grained management fine-grained multi-threading that can be possible, right? So all the threads, because they run the same code. Oh, sorry. So here, this is how we can actually visualize that there are individual threads here, W, X, Y, so on to Z, and we have all of them have one common PC, which will help us to track the instruction that is getting executed and to know where to go, right? And such groups of threads or the warps are actually fed into this SIMD pipeline. Now what happens is, in this sequence at least, first warp 7 will get executed. Maybe it is executing some other set of instructions. They are very much independent to other warps, right? So the order in which the warps get executed and the order in which different instructions get executed across the warps is totally independent. So, and at a very high level, this is how the GPU's internal architecture would look like. So the shader core or the processing element will have the PC and the mask. Mask will help us to decide whether to execute the task or not, right? And it has a small instruction cache within it, and it also has small decoder, which will help to identify the operands and the operation that it has to perform, so on and so forth, right? And because all the warps are executing the same the same instruction, maybe in one particular instance there are some threads for which there was, let's say, a miss for their data item, right? In that case, so if a warp has, let's say, 32 threads, maybe maybe 5 of them were having a miss in their local data cache. In that case, they have to wait to go to the next instruction, right? But the remaining threads here, in this case, let's say the remaining 27 threads, can actually progress. So we in fine-grained multi-threading, right? So these finer level management can happen so that overall throughput can increase more, right? So either the entire so the entire warp will be moved out, and then when the data is ready, it will be moved back into the pipeline, right? Such management is also possible, right? Okay, again, in interest of time, I'll skip this. So we have okay, so this will help us to visualize how different warps are actually getting executed. Okay, so let's say we want to process, of course, even though this says that it's a vector instruction and all, we can replace it with the normal instructions and visualize that we have a group of such registers, right? And with these registers can help us process, let's say, 32 elements at a time. And these 8 lines say that so many processing elements are there, meaning that we have 8 load units, let's say, right? And we have 32 elements to process. So at any given moment, we can load 8 only. So that would be one, right? Immediately after that, we will load another set. In the next cycle, we'll load another 8 elements. And the next cycle, we load another 8 elements, so on and so forth. So after 8 cycles, right, we'll have all the 64 elements to work with. Okay, now then we can do some pipelining to initiate, kick off the next instruction if there is no data dependency, so on and so forth. Right, that's the reason I told that GPU is a mix of both vector and array processors. Okay, so here this is how it would typically go. At any given moment, maybe warp 0 is in the load unit, warp 1 can be in the multiply unit, warp 2 can be in the adder unit, right? Then we can extend the same thing. Warp 3 can be in the load unit after some point of time, and then in parallel warp 4 and warp 5 can also get executed. Okay. Now, to support so many operations in parallel, we also need to have decent memory access. Meaning, if we are able to process, let's say, 32 elements, it means that we need to supply 32 elements. Also, the bandwidth demand on the memory will be very huge. Right, so even there some warp based scheduling can be employed so that we can make better use of the available memory bandwidth. Right, now these warps are actually not exposed to the GPU programmers. Okay, so typically the GPU program will have some serialized portion, and there will be a parallel portion. For the programmer, it is just split into multiple blocks. Right, so there is a serial code, then there are huge number of threads that the programmer will launch, and they are internally grouped as warps and scheduled, right? And then there can be some synchronization done on the CPU front, where again there will be some piece of code that will be executed in serial, and then it can repeat. Okay, now a simple example, of course, Dr. Praveen is going to walk us all with some some more detailed examples. So here the simple example that we currently we're looking at so far is this array addition. We are actually adding nearly 1 lakh elements here, so that can be potentially be done something something like this. We can launch 1 lakh threads, right, with this simple CUDA code. Okay. So again, as an extension of the same thing, we have matrices that we are trying to add. Right, now each thread we need to carefully assign one particular element of A and another one particular element of B. So that's where we use this the variables I and j, which uses block ID, block dim, and thread ID, etc., to generate I and j. And with that, we are actually getting a unique index for each thread. For a given thread ID, we have a unique index. That's how we are able to process multiple of these array elements without any correctness issues or synchronization issues. Okay, now how are these blocks of threads mapped to or converted to the warps, right? So at the GPU core, we have the SIMD pipeline, the streaming processor. Many such streaming processors are there. We can call them streaming multiprocessors also. So this is how a typical streaming multiprocessor would look like. This entire box is a streaming multiprocessor. It has a dedicated instruction cache. It has warp scheduler. It has a dispatch unit that will dispatch the instructions whenever the particular functional units are ready. Then it has a common registry file. Then we have multiple streaming processes like this, right? And there are some dedicated load store units also that can that can be there, and there can be some specialized functional units. That something like multiply and add, or maybe there can be a systolic array itself there, or a TPU within this as part of this SFU. Right now, blocks are divided into warps based on how many threads a warp contains, right? And these warps are now, we can visualize it like this in a two-dimensional fashion, right? So multiple warps are scheduled, right? And there has been a progress on how the traditional SAMD used to work when compared to what's currently deployed, right? So again, in interest of time, I'll skip this. Okay. Okay, so now because we have multiple threads working on the same piece of code, right? Let's say if we have some piece of code for each thread, something like this. So we have a decision A, then we have another decision B, then based on that we go either to C or D, then they can both lead to E and then to G, etc. So from A to G there are multiple different paths that we can potentially take. Now based on, so these are decisions which typically will be based on the data. Now, because each thread is working with its own data, the path it can take can be potentially different. Here is an example where thread 1 is moving from A to B, B to C, C to E, and finally to G. Maybe thread 2 can take this path, A, B, D, E, G, right? Then thread 3 can also take the same path. Thread 4 can go from A to F to G, right? So all these can be within the same warp, right? But how can we handle that? So if thread 2 and 3 are executing B, right, instructions of B, thread 4 is not having that B at all in its path, right? Then the very notion of warp will be lost, because all the threads in a warp should execute the same PC or the same instruction, right? So this is the control flow problem typical in GPUs, and we as programmers need to be very careful and try to avoid it as much as possible, right? This problem is called branch divergence, because even if one thread within a warp will take another path, then all the threads will get impacted, right? They have to go as a bunch, right? So if let's say we have 8 threads, and based on some branch condition, 4 are taking path A and the other 4 are taking path B, even though they all go and converge in a common point, let's say C, right? There is a difference in the instructions these threads execute and the remaining 4 threads execute. So that's what the branch divergence is all about, right? So now how do we handle this problem is with masking. Okay. Okay. Let me go to next slide. So this is called, with masking, and we can also do the dynamic warp formation, right? New warps will be formed. It's not that whatever we started off with, let's say warp 0 is with thread 0 to 31, and then warp 1 is thread 32 to 63, etc. But we notice that some of these threads might be executing different paths. So dynamically, those all the threads that are going taking the same path will be grouped as a new warp. Then there will not be much performance loss. Okay, so let's say we have 2 warps like this, warp X and warp Y, right? And warp Z will be like this. Okay, and so again, so we start we formed a new warp wherein the threads from X and Y are grouped to all these are now following the same path. Okay, now after some time, let's say there was some other warp from which we can we can group again. So here the orange and green threads are now grouped to form a new warp. All of them are again executing the same set of instructions, right? So this is the dynamic warp formation, right? Again, an example. So so let's say this is with one warp, right, where 4 threads were taking path A and 4 threads were taking path B. And in the same way, we can have one other warp. They also will face a similar situation where here we have 5 threads from this orange warp that are executing path A, right? Now a new warp will be formed like this, right, and executed, right? And all the remaining threads will also be formed with another warp which they will take path B. Okay, just a simple example of the same, right? Just illustration and how the so this is would be the baseline warps, right, with masking. But next we will have dynamic warps, something like this, where we are able to make maximum use of the threads, right? So you can see that here 2Cs are getting merged and 2Ds are getting merged into a new warp, and and we are able to work them in parallel, right? So that's how we can gain performance. Okay, and to achieve this, there are few hardware constraints, but in interest of time, I'll skip them, that we need to address. The other problem is the so the long latency memory operations. Okay, because some threads data might be readily available in the cache, but some other threads data might not be available. Now until the data comes back to the SM, we have to stall all the threads of that warp. So instead we can again do what's called memory coalescing. Here there is a scheduling level decision to whenever a particular thread encounters a long latency memory operation, we move on to some other warp, right? And when it comes back, we again get back to its execution, right? Such a scheduling can be done at the memory level also. Okay, so these two are important points whenever we are working with GPUs. One is thread divergence and other is the long latency memory operations. Okay, so let me, in interest of time, go through quickly go through the current. Yeah, sorry, I came out of the. I hope you're able to see the screen. So this is one of the earliest GPUs that NVIDIA has come up with, right? Somewhere in 2008, right? NVIDIA GeForce GTX, 285 core. It has 240 streaming processors, but for all general purpose understanding, we can say that it has 30 cores and each of them has 8 functional units. That's how we have effectively 240 streaming processors, right? And the arrangement is something like this. They all each of the threads also have a local storage, which is 64 kilobytes, right, for the registers, right? And here the warp size is 32, and they have been interleaved in a fine grained manner, like we discussed earlier, right? And so on overall, these many number of threads can be active at any given moment. Okay, now that was one of the initial example. Then over the years, we have come a long way, and currently we have A100, and we'll also see that there is a H100 NVIDIA GPU, right? Basically, the processing capability of each of them has now grown over the time, right? We started off with 240, now we have 5120 stream processors. It means that we can effectively conduct so many simultaneous operations in parallel, right? And this is how the V100 looks like, right? It has 80 cores, right? Each of them, as mentioned, has 64 functional units within it. Okay. Now, we can, with V100, we can process, the throughput can be as high as 15.7 teraflops or 7.8 teraflops for the double precision, meaning 64 bits, right? Or it can be, if we are using the tensor cores that are typically used for deep learning applications, we can achieve a throughput of 125 teraflops. Okay, and tensor core typically is something like this, right? We have two 16-bit floating point units, and we multiply them, and we have an addition. It's like multiply and add kind of operation, right? So okay, let me. I'll skip this in interest of time. This is the one tensor core that is there in Volta, right? And this is the A100, one of the latest, right? It has 6912 stream processors. The way we interpret it is 1082 cores times 64 functional units each. Okay, so this is the view, and this is the maximum throughput that we can achieve, right? Nearly 312 teraflops for deep learning applications, right? Again, the tensor core now has been matured to handle more complex operations, right? And now, so we have the H100 GPU, right? It has 144 cores, right? And it also has 60 MB L2 cache, right? To basically exploit any sort of locality, and to also satisfy the increasing, exploding memory bandwidth requirement. Okay. So again, it has a new tensor core, the fourth generation, and it can handle some more complex operations, right? And look at the throughput that it can achieve. It's nearly 800 teraflops. So this is the last slide, right? The terms that with respect to GPUs that are used are different based on the vendor. Here, for NVIDIA, we use terms like warp, and for AMD, it is wavefront. And in NVIDIA, there is the streaming processor, and we don't have any counterpart with AMD. So the streaming, the N group of N streaming processors is called, will form our SIMD functional unit in NVIDIA, but the same thing is referred to as vector ALU in AMD, right? In GPUs, we have SMs, and in AMD, we have compute unit, CU. Okay, and so the underlying operation is still more or less same, just that the function, the naming is different. Here too, even in AMD sense, we have a group of threads called wavefront, which will be executing the same instruction. And again, we have the fine-grained management of the threads within these wavefronts. And again, there too, we have the issues with the branch divergence, etc. Okay, so with that, I will stop. Dr. Praveen, is that okay?
Yeah, Dr. Kalyan, thank
Yes.
you. Yeah, now I would like to give you a break for around 10 minutes. Please be back by 7:15. In the next session, I would like to cover basic CUDA programs. How can we write CUDA programs right from the scratch? Okay, thank you.
Thank you. We'll catch you again.
Yeah, do you have any doubts?
Yes. Yeah. So yeah, please shoot if you have any questions.
Now I'd like to disconnect this particular one. There is some issue with this Zoom. Okay, please join at 7:15. Okay. Thank you.
Thank you.